thing is
So let's finish off this power supply series. Developing a high voltage regulated variable supply was a lot of fun. I think I have a working circuit. It can be reduced some. There was talk of possibly eliminating the dual current regulation system and having just a single BD139 NPN transistor controlling the current sense. This simple current limiter system seems to work quite well, and we will exercise the box with some different loads, overload condition, and even short circuit conditions in this video. The first thing I want to cover is labeling, how I was able to put the labels on the front of the box. That should be interesting to you guys that want to finish off your projects. You've got painted front panels or maybe even brushed aluminum or anodized front panels. You want to put some labels on the front. I'll show you how to do that with a simple label maker. So this is the final video in the series. We'll do a little bit of cleanup. I'm not going to go as far as to modify the circuit at this point. That's up to you guys to simplify and work with the circuit a little more as you go. Somebody was trying to use the supply at 400 volts for an ART13 aircraft transmitter. That's a little more than the current limit on the sense resistors in this box. So instead of using the 10 ohm resistors, you probably would have to reduce them to get the current that medium supply requires. That's powering up quite a few stages in the ART13. So this guy would be cutting back, probably would be into the overload condition to power the ART13 as it stands with those 10 ohm sense resistors. So that's the only comment I've got on the electronics in the box. Again, you want to run more current, you'll need a bigger heatsink, and you need to take the fan situation a little more seriously. I had several questions from people that were asking, Mike, how did you do the very professional looking labeling on the front of the power supply? Well, the answer is very simple. Photoshop. I just took the picture of the front panel, touched it up a little bit, and then added the lettering in Photoshop. But we really would like to label this thing for real. I mean, it looks okay, but you need to have something on here that lets you know that it's a completed project. It's going to stay on the bench. There are many different types of marking systems that you could attempt with something like this. Everything from fancy laser engraving and machining to some type of a stencil or template that you would spray, silk screening techniques, and so on. But the simplest way today is to use some type of a label maker. And I've got a Brother, it's a fairly generic label maker here. It's a P-Touch, I think it's a 220. And you get the appropriate sized P-Touch tape. It's 1/4 inch, 6 millimeter. It's going to give us black on clear, black print on clear, transparent to the painted front panel, hopefully matching my artist's conception of what the front panel is going to look like. Let's see how successful I can be playing with the label maker to get this thing marked properly. So this is not an arts and crafts channel. There's plenty of those out there, but I've just done one of the labels to show you what you can accomplish on these label makers. You can adjust the font, the style, there's symbols at your disposal, and you have different heights on the tape that you can buy. This is the thinnest tape they make. It's maybe a little bit too small for the set, but I could do most of the small controls and jacks using this size tape, which is the 1/4 inch tape. The 1/2 inch tape would be more appropriate for the label that goes on top that says variable high voltage regulated power supply. So anyway, I'm not going to bore you by going through this whole thing, but just wanted to show you how an ordinary label maker with the clear style tape, black on clear, allows you to mark any painted front panel quite effectively. So I didn't happen to have the clear label 1/2 inch tape for the machine. I had the ordinary black on white, and you can see how terrible that looks compared to using the clear, but that lets you see the difference. I think the clear is a more professional situation with a painted panel. There are more modern machines where you can actually communicate with wireless Bluetooth and USB, and you can do all of this stuff on your PC, but I just did it manually on the label maker, and it took approximately 1 hour. As I buttoned this up in the last video, I just basically made sure that it was working in the case, but I did not go as far as to see if the fan was going to work properly. I didn't put various loads on it to see how it would handle, higher current situations and how the cutback would work with the overcurrent sensor. It looks like we're able to achieve, 50 or 60 milliamps, no problem, even more, before it starts to cut back at the higher voltages. So we still have some of that SOA, that safe operating area stuff going on. And the current sensor is linear, and it's not going to give you the exact answer at all voltages. So this is a very, very simple current limiting circuit. Also, the short circuit will be a little higher than if we instituted a foldback system. And I'm going to go over the foldback system a little bit later in the video. So right now, I'm going to take the cover back off, and let's see if we can get the fan straightened out. Remember, we have a sensor in there that's supposed to turn the fan on. I have modified the voltage on the fan circuit to come off an LM7809 regulator. Originally, I had it on the unregulated 7.5 or 8 volts right at the bridge rectifier. Now it's going to be regulated. We need to see if the fan comes on and turns off without any variations or oscillations or noise or problems in that linear region. So let's get the top off this thing, put some real loads on it. Also, I have to figure out how to attach my temperature sensor to a now very hot heatsink, 600 volts on that heatsink. So how do we attach this temperature sensor to that heatsink without causing an explosion or worse and ruining the instrument here? And then we'll see if the fan comes on and the fan turns off. Okay, I have the temperature sensor connected, and I've taken some precautions to make sure that the probe is not at 600 volts. Not trusting the anodize of the heatsink, I've taken one of those old-fashioned TO3 insulators, and I wrapped it around the tip and then jammed the tip in between one of the fins near the temp sensor. Now, it's on right now, so let's touch the voltage probe and verify there's 0 volts on it. Okay, so we are insulated. So I'm going to be connecting that 6K load to the output of the power supply, and we'll have it turned up to maybe 350 volts. And let's see if that fan will come on. Okay, the load is connected. Let's turn this thing on. And let's start bringing up the voltage until we get some good current drain. 300. Okay, there's 350 about. That should heat those transistors up. Let's see how long this takes. Okay, about a minute and a half in, and the temp sensor is beginning to move. I wonder how good my thermal connection is to the heatsink. We knew that the fan turned on somewhere around 39 C, so let's see if it's going to turn on. Okay, we're 3 minutes in. The sensor says 30, but no doubt with that insulator it's lagging. There it comes. So the sensor says it turned on at 31, and before we were noting about 39, so I'm not sure how good my connection to the heatsink is. Well, whatever the differential is, it's steady. Looks like it did stop it from climbing because it was as high as 31, now it's back to 30. So the heatsink is certainly not getting any warmer. The fan is keeping up with it. Remember, this is an exhaust fan. It's pulling air away from the heatsink. Looks like we have stability. So next I'm going to turn the high voltage activate switch off, and we'll see if the fan stops. I am noting that the fan RPMs are starting to go down about a minute into the activate being off. Control is smooth so far. Okay, 3 minutes into the cool down cycle, the fan has stopped. Okay, so now I have a 2000 ohm 35 watt load. And we're going to try the same thing. Let's definitely make sure we're in current limit. Let's try 200. That's about it. Okay, that's 200 volts at 100 mils. So that's a good 20 watt load. Okay, fan came up in 50 seconds, 50. Temperature continues to climb on the heatsink. So the efficiency of the fan blowing out appears to not be very good. It might be a little better with the box because the vents on the sides might direct the airflow a little bit better. If the fan were blowing in on the heatsink, that might be better as well because that's going to definitely move air across the fins better. So reversing the direction of the fan might be worth it. It's still slowly climbing. Likely in the 40s, since our sensor is not well coupled to the heatsink. And boy, it's hot. I will tell you, the load is very hot. Okay, I've had the switch off and the fan operating now for about 3 minutes, and it is bringing the temperature down. So there's no doubt the fan is not that effective with the heatsink in the exhaust mode without some type of venturi or other wind tunnel arrangement that would suck the heat out of the heatsink. Some type of plenum is required to make this type of exhaust fan effective. Okay, now after about 4 minutes, it's starting to go down. Looks like the fan will turn off soon. Again, this was an overcurrent condition at 300 volts, putting out 20 watts constant, and the fan was really not able to keep up with it. So there are several ways to solve this fan issue. One would be to have a more effective fan, definitely putting the air right on the fins. Making a wind tunnel forces the air through the fins and out the exhaust fan. That would work. Perhaps blowing into the fins and then having some vents on the top of the chassis so that the hot air has a place to escape straight up. So that's fan blowing in, maybe some holes over this area here so that the hot air is coming up like this. Okay, this is where we kind of started this project, right? I had the TNT oscillator transmitter, and I needed a power supply to be able to power it up. The TNT requires 7.5 volts to light up the Type 10 tube, and we have that on our front of our power supply, 7.5 volts regulated, and it is indeed lighting the tube. However, the TNT uses center tap keying. Center tap keying to ground assumes an isolated transformer or an isolated DC supply, isolated from ground. So another microwave 1 error in the power supply design is that I referenced the filament voltages to ground. Now these work perfectly with regenerative receivers, where normally it doesn't matter if your filament is referenced to ground or not. The receiver's always on, in other words. That's an error in the power supply design. It lights up the tube and it also keys the transmitter at the same time. So when we turn up the voltage, and now I'm talking about the high voltage, it's transmitting, putting out power already. Okay, she's putting out 4 watts now continuously. 4 watts continuous at 400 volts, drawing 50 milliamps. The fan is not on yet. I want to light this thing up with AC and see if we can key it normally. Okay, we now have the filament lit with my isolated power supply, and I'm at 400 volts. Ooh, that sounds pretty good. Watch the meter over here. Well, there's something loose, but you get the idea. If we had some stability on the table, it would sound pretty good. Let's see if we can take it all the way up to 500 volts. Remember, that was the original rating on the TNT. They wanted you to put 500 volts on it. That's crazy. Okay, over 6 watts on the TNT. It's really cranking. It really likes the regulated supply too. Wow. So let's look at the regulation. Remember, this is a follower type voltage regulator, which is the most primitive type. So let's just adjust that. So we've got a number to look at. 200.5, 199.2. It's pretty good regulation, for just a follower. There is no feedback. This is an open loop regulated power supply. There is no feedback. That's pretty good regulation. Let's take it up to 400 volts. Okay. Okay. We've dropped about 10 volts. That's because we're into the current limit already. This particular supply with this particular transformer and those particular resistors that are used for current sense will not allow much over 70 milliamps before it starts to cut back. So it's cutting back the voltage about 10 volts. For a general on-the-bench type thing where you're just powering up a receiver or a 1 or 2 tube transmitter, or where you're keying it and it's not constant drain, this supply is plenty adequate. There's a 1500 ohm load with 50 volts. It's pretty good regulation. Let's bring it up to 100 volts. Okay. That's starting to dig in now. That's about 75 milliamps of drain. And of course, if we're at high voltage at this low load resistance, it's really going to go into limiting. That really brings it back. And it didn't take long for the fan to come on. The fan's winding down after a couple minutes, so we're going to try a direct short circuit at 200 volts. Okay, and now the one you've been waiting for. We're going to go all the way up. This should pop it. 500 volts. Short circuit. It survived it. We love that.
So wow, I guess the message about heat sinking and fan has come through loud and clear. You really have to take thermal seriously. Sometimes you have to grossly overdo the heat sink and fan. Otherwise, you need to increase the value of the sense resistor and reduce your constant DC current limit. High voltage regulators get easier with fixed voltages or limited ranges because you can tailor your input voltage to be only 30 to 50 volts above your target voltage. This naturally limits your pass device's dissipation needs. So let's consider a fixed application like that ART13 medium voltage. They suggest 400 volts at 350 milliamps. I've actually run the ART13 medium voltage as high as 450 volts. So anything between 400 and 450 volts at 300 milliamps, that's your target. So starting with an input voltage that's just slightly higher is a great way to simplify things. In other words, if we want 400 volts, we don't want 700 volts on the input. We'd like to have maybe 450 volts on the input or 475 volts on the input. That takes it easy on the pass device, since you only need to drop, 30, 40, 50 volts, and that keeps the dissipation below 20 watts. So Then the current sense resistors can be dropped to something more reasonable. This increases the cut-in to maybe 400 or 500 milliamps before the voltage starts to be reduced.
The foldback circuit allows the current limits of the sense resistors to work fairly normally until you get closer to that short circuit or extreme overload condition that we had. 300 volts and the 2000 ohm load. The 20 watts was more than this thing wanted to supply. In that case, with this foldback circuit, the two devices are clamped into being shut off much sooner in the event of a short circuit. Less static current drain. So let's go through that next. Let's talk about this foldback circuit. I am not going to solve the fan issue, nor am I going to build the foldback circuit, but we will go through how the foldback actually operates.
Okay, I saved this for last. This is the most controversial and difficult subject of this video. Foldback. Let's talk about foldback. As opposed to constant current limiting, in normal constant current limiting mode, it's working nicely for our MOSFET, by the way, we provide the designated output voltage and maximum current up to a safe threshold before the limiter device, that BD139, turns on at all. During the short circuit, the device shuts down very nicely because the MOSFETs are nicely voltage controlled. The problem is that the control device, that transistor, the BD139, does not turn on with a very abrupt knee to protect the MOSFET during the mid-range or the severe overload condition, like for instance a 1K or a 2K load, and maybe you're set for a couple hundred volts. Lots of active power dissipation is happening. Even though we've brought down the voltage, you still have the current, and this tempts thermal runaway. It's easy to violate the safe operating area, or SOA, of the MOSFET in this overload condition. Lots of heat is generated, as we saw. So let's review the standard constant current design. It uses the sense resistor and a transistor, like an NBN base junction transistor, to steal base drive from the main pass transistor. When the voltage increases across the current sense resistor, in our case, we short out the voltage from gate to source in our MOSFET implementation. This works beautifully as long as we have enough heatsink to handle the simultaneous voltage and current in the linear region during the protection event. Constant current limiting maintains a fixed current level regardless of the load resistance, which can cause higher thermal stress during prolonged faults. In our case, the voltage is greatly reduced. Our devices seem to survive with a decent heatsink. A disadvantage of constant current limiting is to obtain sufficient safe operating area. The pass element must have a much higher collector current capability than needed for normal operation, and you're going to need a large heatsink. With true foldback current limiting, you reduce the short circuit current more abruptly than in constant current limiting. Again, foldback is defined as a sharp turn-on knee that can reduce the output voltage and output current more abruptly than simple current limiting. This potentially allows the use of smaller pass devices and smaller heatsinks. So we're going to do this by adding just two resistors to the circuit. Okay, let's note that resistors R1 and R2 have been added to the constant current limiting circuit. Under normal conditions, Q2 is off. The voltage divider action of R1 and R2 cause a voltage drop across R1, with the upper end being the most positive. As the load current increases, the voltage drop across R sense increases, as it always did. However, the voltage across R sense must not only exceed the turn-on voltage of the base emitter junction of Q2, but in order to turn Q2 on, it must also overcome the added voltage across R1. Once this point occurs, however, Q2 begins to conduct and reduces the conduction of Q1. This, of course, causes both the output voltage and the base voltage of Q2 to decrease. However, and here's the big effect, because the base voltage of Q2 is obtained through a voltage divider, it decreases more slowly than the output voltage from a heavy load. And because the emitter of Q2 is connected to the output voltage, it must also be decreasing faster than the base voltage. This causes Q2 to conduct even harder, further limiting the output current. Q2 basically gets turned on faster, and the pass device is more abruptly turned off. The addition of the voltage divider components has one disadvantage worth noting. They're directly connected to the high voltage, so it's really another load. Therefore, it's always wasting power, and the resistors, especially R2, can become large. The beta of the protection transistors becomes more important if you do scale the resistor values up, in other words, making the resistors a higher value but smaller size. Let's go through an example at high voltage with reasonable voltage divider current. We're going to need to define some terms. Vout is the regulated output voltage under normal operation. This is the NPN emitter after the sense resistor. VBE is the base emitter turn-on of Q2. Usually this is between 0.6 and 0.7 volts. Our sense is the sense resistor value. With 10 milliamps and 0.68 volts, the sense resistor is 68 ohms. It's a standard value, but notice it's 10 times larger than our original constant current resistor. In the standard constant current limiter, that is no foldback, a 6.8 ohm sense resistor is exactly what you need because the transistor relies solely on the raw voltage drop across our sense to reach that 0.6 to 0.7 volt turn-on threshold. However, when you add the foldback capability and want, say, 10 milliamps as a short circuit limit, we have to introduce a larger resistor. We introduce a resistor divider R1 over R2 that changes how the transistor behaves. R1 and R2 form a voltage divider. I-knee, also called I-max, is the knee current, which is the maximum current designed before limiting begins. And I-short circuit is when V0 is 0 volts. Finally, K, the voltage divider ratio, or the fraction of the output voltage fed back to the transistor base. So let's design for 300 volts DC. We know this is a problem area where we have high dissipation. For instance, if we have a heavy load. We have to be able to handle 30 watts of dissipation continuously. So first let's set the knee current to 100 milliamps. And let's make I short circuit 10 milliamps. So 600 volts times 10 milliamps is 6 watts. That's a very safe short circuit dissipation condition. At 100 milliamps maximum current, the 68 ohm sense resistor drops 6.8 volts. This higher voltage drop is going to hurt our open loop regulation, of course. This is another reason that multiple circuits in parallel might be better, or even resorting to conventional feedback. I've been avoiding conventional feedback, but maybe it's starting to make more sense. Let's set the total divider resistance to around 100K to keep the resistors smaller in the divider. Only a few milliamps are required in the divider with a decent transistor for Q2, so this limits wasted power. So R1 plus R2 total should be around 100K. Consider a voltage divider of R1, say 1.5K, and R2 100K. This ratio turned out to be close, but I played with the math and worked on that divider a little bit, and I found that a 2K and 100K worked out better for our circuit. I would suggest using a higher voltage transistor with the foldback, maybe an MJE 340 or the higher voltage transistor that we took out of the ATX power supply. I want to look at 3 conditions with our new foldback circuit. We actually do the peak current knee calculation first, the control transistor is just turning on, and we think about turning off the MOSFET. So here we are. We're at 300 volts DC at 100 milliamps, right at the knee. So number 1, peak current knee condition. 300 volts on the output, which is the emitter of the control transistor after the sense resistor. Our goal is an R1 and R2 voltage divider that results in approximately 0.7 on the base to emitter junction of Q2 at 100 milliamps output. After some iteration, rather than strict algebra, I got R2 as 100K and R1 as 2K. This set up a voltage divider ratio of 0.98037. Ohm's law says that 300 volts divided by 102K is around 3 milliamps through the divider. So a resistor of about 1 watt will work fine. Let's use a pair of 1 watt resistors for the divider. So here we go. 300 volts plus 100 milliamps times 68 ohms is 306.8 volts at the source of the MOSFET. So 300 volts out and 306.8 volts is now divided down for the base of the NPN. 306.8 volts times 0.98037 equals 300.78 volts. 300.78 volts minus 300 is 0.78 volts. That should be just turning on the transistor. The NPN triggers right at the 100 milliamp knee point, forcing the power supply to enter foldback protection, and if the load attempts to draw any more current, it continues to reduce the current. 2. The short circuit condition. Okay, a short. Basically, the NPN emitter is sitting at ground or 0 volts out. Voltage at the MOSFET source is 10 milliamps times 68 ohms or 0.68 volts. Voltage at the NPN base, scaled down by the R1-R2 divider, is 0.68 volts times 100 divided by 100 plus 2K, which equals 0.68 volts times 0.98037, and that equals 0.666 volts. That sounds kind of frightening. The result is that the NPN turns on, stealing drive voltage away from the MOSFET and holding the short circuit current to 10 milliamps. So here's the question: why is the 10 milliamp condition requiring less VBE than the 100 milliamp condition? What's going on here? I'll come back to that. So the normal 50 milliamp current, which is below the maximum current knee, is the third condition. This is normal output below the knee. 50 milliamps times 68 ohms is 3.4 volts. The voltage at the MOSFET source is 3.4 volts plus 300 equals 303.4 volts. The NPN base voltage equals 297.444 volts. VBE, therefore, is 297.444 minus 300 volts. That equals negative 2.55 volts. Now, because VBE is negative bias, the NPN transistor is heavily cut off. It cannot limit the voltage to the MOSFET's gate. So 300 volts at 50 milliamps is steady and ready at the output. That's 15 watts of dissipation. All is fine. Okay, some of you may have guessed that I'm getting help from AI, especially in the calculations and orderly explanations. Actually, some of my subscribers are adept at circuit work and can do this simple DC stuff on a napkin. But some of us need a little more help to understand new concepts and actually turn them into practical circuits. And the ease of doing diagrams and plots, I have to admit, AI is very, very helpful. So let's get back to that 10 milliamps condition versus the 100 milliamp VBE condition on Q2. This does not make sense. Why would the control transistor need more voltage on the base to limit to 10 milliamps than to limit to the 100 milliamps at the knee? So we have to think of the 0.78 volt calculation not as the transistor naturally resting at that voltage, but as the circuit's attempting to force the transistor's base to 0.78 before it can successfully start the foldback process. Because the silicon PN junction cannot realistically sustain a 0.78 base emitter junction indefinitely without melting or drawing a massive base current, what actually happens in physical reality is the current thresholds shift. The circuit will actually begin to limit current slightly before 100 milliamps. We've already seen that. As the load demands more current, the transistor turns on. It begins stealing gate drive, and the 300 volt output rail begins to sag. The moment the output voltage drops even slightly, maybe to 299 or 295 volts, that massive 300 volt baseline suddenly disappears. The required turn-on voltage relaxes, and the circuit rapidly accelerates or snaps down the foldback curve toward the 10 milliamp short circuit limit. So it's really a paradox, not easily observed or explained in static conditions. You need to have an active model simulator to go through this. The transistor requires a higher apparent bias voltage at the 100 milliamp knee because it has to overcome the massive voltage division of the 300 volt output rail. At a short circuit, that 300 volt roadblock disappears, allowing the transistor to clamp the circuit tightly at a much lower sense voltage.